Welcome back to my video. My name is Ayush Kumar. My USN is 1VE23CS022, and I'm from second semester. And my section is Audi. My subject is Mathematics 2 for CSE stream, and my subject is my subject code is BMATS 201, which is basically BMATS 201. Uh, so my topic is Introduction to Vector Calculus. So, what is a vector calculus? Vector calculus is a powerful mathematical framework that extends the concept of calculus to vector valued functions and fields. It provides tools for analyzing and manipulating multidimensional quantities, making it essential for fields like computer science, physics, and engineering. Vectors and vectors field. Vectors are mathematical objects that have both magnitude and direction, allowing them to represent physical quantities like force, velocity, and acceleration. Second one, vector fields are collection of vectors assigned to every point in space, describing how a vector valued quantity such as electric or magnetic field varies through a region. Visualizing vector. Vector can be visualized using arrows where the length represents the magnitude and the direction represents the orientation. Scalar and vector functions. Scalar functions. Scalar function map a set of input varies to a single real number, such as temperature or pressure, as a function of position. Next, we have vector functions, which is basically the main part. So, vector functions map a set of input variables to a vector, such as a position, velocity, or acceleration of an object in 3D space. Visualizing functions, which is the third thing. Scalar functions can be visualized using 2D or 3D graphs, while vector functions require more complex visualization, such as vector fields or streamlines. So, next we have differentiation of vector functions. So there are basically three types. Which first is partial derivatives, gradient, and the Jacobian matrix. So the first one, the matrix, the partial derivation of a vector function describe how the vector changes with respect to each individual input variable. Gradient. The gradient of a vector function is a vector field that describes the direction and rate of change of the function. Jacobian matrix. The Jacobian matrix is a matrix of all the partial derivatives of a vector function, and it is a key tool in the vector calculus. So the differentiation of vector functions are done. Next we have gradient, divergence, and curl. So the first one which we have is a gradient. So gradient. The gradient of a scalar field is a vector field that points in the direction of the greatest rate of change of the scalar field. Let me repeat that. The gradient of a scalar field is a vector field that points in the direction of the greatest rate of change of the scalar field. Next, we have divergence. The divergence of a vector field is a scalar field that describes the density of the outward flux of a vector field from the infinite simul volume around a given point. Curl. The curl of a vector field is a vector field that describes the magnitude and direction of the rotation of the field around a given point. Next, we have line integral and path dependence. So first, line integral. Line integrals calculate the work done by a vector field along a curve or the flux of a vector field through a curve. It is either along a curve or through the curve. Okay. So the second one which we have is a path independence. If a line integral is path independent, it means the value of the integral only depends on the endpoints, not the path taken. So it basically depends on the paths. It depends on the endpoints of the given integral, not on the paths taken. So potential function, which is the third one. Path independent line integral are related to potential function, which describes the underlying scalar field that generates the vector fields. Next, we have surface integral and flux. The first one which we have is a surface integral. Surface integral calculates the flux of a vector field through a surface or the work done by a vector field over a surface. Next, we have flux. Flux describes the rate of flow of a vector quantity such as the electrical or magnetic field through a surface, divergence theorem. So the third one we have under the surface integral and flux is the divergence theorem. The divergence theorem gives us how we can relate the flux of a vector field through a closed surface to the divergence of the field within the surface. So it basically is a vector field through the closed surface to the divergence of the field within the surface. It's given. So if we have a few theorems, so theorem on vector calculus. So the fundamental theorem of calculus are Green's theorem, Stokes theorem, and divergence theorem. So first we'll take the Green's theorem, which is relates line integral in the plane to surface integrals. Stokes theorem, a related line integral to surface integral for vector fields. Divergence theorem relates surface integral to volume integral of the divergence, not the divergence field. Next, we have applications in computer science and engineering. So, what vector calculus? It uses the model and manipulates the 3D shape, lighting, and camera perspective in computer graphics and visualization. Fluid dynamics. Vector fields are used to describe the flow of fluids such as air, water, which is essential for engineering applications like aerodynamics and hydraulics. So the things which I mentioned, which are basically such as air and water, and the flow of fluids can be measured using the vector fields and along with the help of physics also. Next we have electromagnetism. Vector calculus provides a powerful framework for analyzing electrical and magnetic fields. It is crucial for the design of electrical system and devices. So that's it for the video. I hope you like the video. If you have liked the video, surely give a like button and let me know how the video was and the comment section. That's it for the video. Thank you.